Section 6.6 is function operations. I can add, subtract, multiply, and divide functions, and I can find the composite of two functions. Those are our learning targets and what we're shooting for in this section. Big idea for this section. Functions can be added, subtracted, multiplied, and divided based on how these operations are performed for real numbers. One difference, however, is that we have to keep in mind the domain of each function. The diagrams on the bottom of page 399 shows what happens when we apply one function after another function. The output of the first function becomes the input of the second. When we combine two functions in this way, we form what's called a composite function. So the take note on page 400 talks about composite functions. The composite of function g with function f, we can call g of f or g composed with f, is written like this. Keep in mind that little circle isn't multiplication. Okay, it's a little circle. I don't know why they use that, but they do. Or we can write it as g of f of x, which is g of, instead of putting x, we put f of x. That's our input, where we evaluate the inside first and use the result as the input of the outside function. So it's kind of like when we work with PEMDAS, when we have two sets of parentheses, we have to do whatever's inside, most inside first. Same idea here with these composite functions. Here I have to find g of this whole thing first. So I need to know what f of x is. So this is my first step. Then I can find my g. When I look g of, I say f of x. And so that has to be found before I can find g. If we write it in this notation, it's like we're finding backwards. G of f, I still need to know what f of x is, so I plug my value in for f. Whatever I get there, I plug into g. So in example 3 here, composing functions. F of x equals x minus 5, and g of x equals x cubed. We're going to figure out what is g of f, or g composed with f, of negative 3. We have two methods here. So the first one, we can take negative 3, and I'm looking for g of f of negative 3, which means I need to know what f is first. So I take negative 3 and I plug it in to f. So remember, this replaces our x. So everywhere I see an x in f of x, I replace it with negative 3. So f of negative 3, or the value of my function with an input of negative 3, is negative 3 minus 5, or negative 8. Now, I take that value and I plug it in for g, because I want to know the value of my function g based on the value of my function f. So for g of x equals x cubed, I take my f value and plug it in everywhere I see an x. So I have g of negative 8 equals negative 8 cubed. All I did there was take this negative 8 and plug it in for x. And I can evaluate here. So I can rewrite this one more time as g of f, or the value of g based on f, g composed with f, of negative 3 equals negative 512. The other way we can do this here, guys, is I can rewrite this as g of f of negative 3. And that means on the outside I start with g. So I take g and I substitute in f of negative 3. So I'm going to take my f of x first and substitute f of x, which is x minus 5, into g of x. So instead of having x cubed, everywhere I used to see an x, now I write f of x, or x minus 5. So x minus 5 cubed. I write my composite function first, and then put my value in. Here I'm specifically looking for -3, so I substitute that in for x, -3 and -3. G of f of -3 gives me -3 minus 5 cubed, which is -8 cubed. So the value of g based on f and our evaluating it for -3 gives me -512. Either way here. Here, same idea. We just want to know what is f composed with g, or f of g. So here, again, we have two different ways. You only need to do them one way. I'm just going to do them both again so you can see them both and pick which way you prefer. There are some times where we have to do it by substituting in our entire function and then evaluating. Like if we didn't have a number here, if we had a variable, or if we were just looking for the composite function itself, not evaluated at a specific input, then we would have to substitute in the entire function instead of just the value. Here, I'm looking for f of g of -3. So before I can find f, I need to know what that g value is. I plug -3 into g first, into the closest thing there. So everywhere that I see an x, I plug in a -3. Now that I know what g is, I can substitute that value in to f. So I look at my function f of g, which is -27. Everywhere I see an x, I put in my g value, -27. And here I get -32. So the value of f of g of -3 is -32. We also could have done this the second way. I can write this as f of g of -3. F of g of, instead of x, we have -3, which means I'm going to take my function f of, everywhere I see an x, I'm going to plug in g of x, because I have f of g here, so I'm going to plug in g of x, which I know is x cubed. So f of g of -3, first I'm going to do it with just the x to show you here. So everywhere I see an x, I put in x cubed. I see an x, I put in x cubed, and then I bring down the rest of our function here. Now I can substitute in my value. -3 is x, so I plug it in for x. And f of g of -3 equals -32. And we can write this in this format still if we want to. It doesn't matter, they're interchangeable. They mean the same thing. Either way, we get -32. In example 4, it says, you have a coupon good for $5 off the price of any large pizza. You also get a 10% discount on any pizza if you show your student ID. How much more would you pay for a large pizza if the cashier applies the coupon first? So we have two options here. Okay, our cost for the pizza based off our coupon is our pizza cost minus $5. And the cost of our pizza based off our discount is our pizza cost times the percent we're paying. Here, if we're not paying 10% out of the whole thing, we subtract there and we are paying 90%. So times 90%. I'm going to rewrite this, guys. 90%, I get rid of my percent sign and move my decimal 2 places, is 0.9 times p. So we have two options. The cashier can either do coupon first and then our discount, or they can do the discount percent and then the coupon. So if we do coupon first and then the discount, okay, we're taking our discount based on our coupon. If we do our discount first and then our coupon, we're taking our coupon price based off our discount. So our options here, C is P minus 5. I substitute that in. 2D. So I'm still going to multiply by the 0.9. I distribute 0.9p minus 4.5. And this is coupon, then discount. If I do the discount and then the coupon, I take my discount, and whatever number I get there, I plug in to the coupon. So that's my p value minus 5. Here, there's nothing to multiply, so it's just 0.9p minus 5. So if I compare these, think about these as dollars. I'm paying 90% for my pizza either way. This part is the same. The amount that's changing is my dollar amount. Here, I subtract $4.50. Here, I subtract $5. So the difference between those is 50 cents. So if we do the coupon first and then the discount, we have to pay an extra 50 cents versus doing the discount and then the coupon. Okay, here it works out as subtracting $5. Here it only works out as subtracting that $4.50. So it's an extra 50 cents that we don't get to save. Now, a store is offering a 15% discount on all items. So the store discount, if we're not paying 15%, we are paying 85%. So the cost based off the store item is our normal price times 85% or 0.85. Also, employees get a 20% discount. So we have 20%, which means just from the employee discount, we're taking the price times, there's an extra 80% there, so 0.80 or 80%. So E is going to be 0.8p and S is going to be 0.85p. We want to take the 15% discount, which is the store discount, and then the employee discount. So we're going to take our store discount, and whatever we get for that, we are going to substitute in to E, which means I'm going to have 0.8 times our p-value here. And since all I'm doing here is multiplying, I can multiply right away and get 0.68p. What that means, guys, is that we're paying 68% of our price, the original price. Now, to model taking the 20% discount and then the 15% discount here, remember my store is 0.85p and my employee is 0.8p, 80% of my price. So we want to take the 20% discount, which is the employee discount, and then the store discount. So we start off with our employee discount, and whatever value we get for that, we substitute in to the store. So whatever value that is, we plug in for p, which means we'll multiply by 0.85p. Here, all we're doing is multiplying, and again, we're going to get 0.8 times p. So it doesn't matter, guys, which order when all we're doing is multiplying. But anytime we're doing adding and subtracting and multiplying and dividing, the order does matter. We can do multiplication in any order, though, so since these are both multiplying, it didn't matter the order that we took them. Recap here. Functions can be added, subtracted, multiplied, and divided based on how these operations are performed for real numbers. One difference, however, is that the domain of each function must be considered, and that's all for 6.6.